Hi, this is Alex from devstories.eu. Astropy, Python for Astronomy, episode 10 of 15. If you slice a standard numerical array, you only get raw pixels out. But telescope data is never just a matrix of numbers. When you crop an image to look at a single star, your error bounds, your dead pixel masks, and your sky coordinates must stay perfectly aligned, otherwise your entire analysis breaks. That is exactly why we use gridded data, the NDData and CCDData classes. At its core, Astropy provides the NDData base class as a standard container for gridded astronomical data. While NDData handles the general structure, for actual optical or infrared images, you will typically use its specialized subclass called CCDData. This container exists to tie your raw pixel values directly to their physical properties. Let us walk through initializing a CCDData object for a raw telescope exposure. You do not simply pass in a two-dimensional grid of numbers. You pass the raw data grid, and you must assign a physical unit, such as electrons or analog to digital units. Next, you attach a Boolean mask. If a high-energy cosmic ray strikes your detector during the exposure, you flag those specific ruined pixels as true in a separate mask array, and you hand that directly to the CCDData object. Then comes the error tracking. You attach an uncertainty array. For our raw image, you might calculate the Poisson noise and attach it using either the standard deviation uncertainty class or the variance uncertainty class. Now, your brightness values, your units, your bad pixel flags, and your statistical noise limits are locked together as one unified object. This brings up a common confusion. Once you have this fully loaded object, do not try to use standard mathematical operators like a simple plus or minus sign to process the image. If you attempt normal array arithmetic to subtract a dark background frame, you will leave your uncertainties behind. Instead, you must use the built-in arithmetic methods provided by the class, such as the add, subtract, multiply, and divide functions. This is where it gets interesting. When you call the subtract method, Astropy does not just subtract the pixel values. It automatically propagates your variance uncertainties through the operation, using standard statistical rules, yielding a mathematically sound noise profile in the resulting image. Later in your workflow, you might realize your full telescope image is too large, and you only want to analyze a single galaxy located in the top right corner. You accomplish this using a tool called Cutout 2D. You provide your main CCDData object, the exact center coordinates of your target galaxy, and the bounding box size you want to extract. Because you packaged everything in a CCDData container, Cutout 2D handles the complex syncing automatically. It returns a new, smaller object. It slices the pixel grids, but it also automatically crops the cosmic ray mask and the variance uncertainty array to the exact same dimensions. Crucially, it translates the underlying world coordinate system. The pixel coordinate 00 in your new cutout correctly maps to the exact same right ascension and declination as it did in the master image. By treating the pixel data, the physical error margins, and the spatial coordinates as one indivisible unit, these classes prevent silent data corruption as your image moves through complex analysis pipelines. That's all for this one. Thanks for listening, and keep building.